It's recording.
Hi, and welcome to our Module 4, Chapter 11, Teach. This chapter, we're going to go over transformations, symmetries, and tillings. And my name is Sarah Vernig.
I'm Courtney Snyder.
I'm Taylor Richardson.
Okay, Demia, what rotation did Devante and, I'm going to say this wrong, Ephraim use?
Okay, I'm glad you asked. So with this one, I kind of had a few problems with it, with the rotation. So once I understood how to do it, I think I needed to go over how to explain it. So if you look right here, you see the two figures. So if you pay attention, the one on the left, you have your two triangles at the top and then the square second. And then if you look at the one on the right, you have your triangles at the bottom and then your square as the third figure. So as you know, if you do a complete circle, that's 360. But if you look how this has basically just flip-flopped, you realize it's just flipped one half of the 360, which will give you a 180-degree rotation. So for that answer, they did a 180-degree rotation. Courtney, can you tell me what would this figure look like if it was reflected over the line of reflection?
I sure can. Okay, the line of reflection that we're going to use is this line right here at the bottom of the figure. And now a simple way to just remember this is what we're wanting to know is what would this figure look like if we simply just flipped it completely over this line right here. Now what we know about reflection is that each point matches up exactly same measure-wise from the line of reflection here. So this point here is going to be the exact same distance over here when we flip it over. The same with this point and this point. And then our farthest point away is going to be the same distance away. We're going to do that with each angle. And when we flip it over, after flipping over the entire figure, it's going to look exactly like this. And each point is going to be in the same distance, just flipped over. Like if you're folding a piece of paper in half that has this stamped on it, it's going to be stamped back this way. What should the reflection look like, Sarah?
Okay, so when we reflect it, means that we're not going to flip it because flipping would give us a different picture altogether. What we need to make sure is that when we flip it, these green triangles are going to be pointed the same way. So we want both of them to be pointed to the right. And that's how we know what our reflection is going to look like. Oh, and there's my line of reflection. So that's how you know too is you're going to look at that. Okay, Taylor, can you show me the difference between a rotational rigid motion and a reflection rigid motion with this shape?
I sure can. That's a great question, Sarah. With rotation rigid motion, you want to think of it like you're holding onto the shape from a certain point right here. And it's going to turn about that certain point. Whereas with reflection, you're going to flip or reflect the shape across a certain line. For this example of rotation, we're going to hold the point right here, and we're going to rotate it 180 degrees this way. When we do this, the shape will look like this. And then we're going to look at reflection. And with reflection, we're going to place our line of reflection right through the square, right through the middle of the shape. And we are going to just flip it right over this line. And when we do so, our shape will then look like this. Demia, if I can only have one line of symmetry for a triangle, what would it look like?
Okay, first I'm going to show you two triangles. And on the one on the left, we're going to have a line of symmetry going through the middle, going horizontal. And then on the one on the right, we're going to have the same line going up and down. So basically, for a line of symmetry to be correct, it's basically saying you're going to have a piece of paper, you're going to fold it in half. And if I fold that in half, will it be even on each side? So if I was to take this triangle on the left side and fold it down, these would not match up. So this one would not be the correct way of the line of symmetry. But if you look at the triangle on the right and you flip it over, all the edges and all the sides would line up. And so that's how you know the line of symmetry, what it would look like for that particular triangle. Courtney, can you tell me if these figures have rotational symmetry?
I sure can. The first figure we're going to start out with is our diamond. And what we know from rotational symmetry is if I took this diamond right here from this point and turned it 180 degrees, would it look the same? Now with the diamond, it would. When we turn it 180 degrees, this shape is going to look the same afterwards as it did from the beginning. Now we're going to move on to a triangle. Sorry, got a little ahead of myself. So this triangle, if we started with this point and moved it 180 degrees, it's not going to look the same. It looks like it just reflected over a line of symmetry right here, but it does not have rotational symmetry. Now we're going to do this hexagon, and if we grabbed it right here in the center of this line and turned it 180 degrees, it's going to come out looking the exact same. Sarah, what's rotational symmetry but not reflection symmetry with these shapes?
Okay, so rotational symmetry is whenever we turn it 180 degrees, but reflection symmetry is whenever, like, we're going to look at it in a mirror. So these shapes here do not have reflection symmetry, but they do have rotational symmetry. So whenever we turn it, let's see, we're going to do 90 degrees first, and if it will show, give me just 1 second, it's not wanting to turn. There we go. So we have 90 degrees. So these are our 4 shapes. When we turn them 90 degrees first, they look pretty similar. And then we're going to turn them the rest of the way. We're going to turn them the 180 degrees. So we're going to make sure that these shapes look like what we started with. And as you can see, the rectangle is the same, and all of them are the same. Now these 2 other shapes that look kind of questionable, they have reflection, or not reflectional, because if we looked at them through a mirror, they're going to be flipped, and that's not what we're looking for. We're just taking them and rotating them 180 degrees, not 360. We don't do a full circle. We just want to do a half of a circle. So these are our 4 shapes that have rotational symmetry. All right, Taylor, which of these figures have no line of symmetry but still have rotational symmetry?
I am so glad you asked. Okay, a shape has a line of symmetry when a shape can be folded in half a certain way and it looks identical to the other side. Rotational symmetry occurs when a shape can be turned a certain degree and it still looks like the original shape that we had. So for this question, we first want to eliminate our shapes that do have lines of symmetry. And so when we draw our lines of symmetry, we see that all of these shapes have lines of symmetry, so we're just going to go ahead and wipe them out of here. So we're left with these 2 shapes, and we want to see if they have rotational symmetry. And this is the point when, if you have paper cutouts of your shapes, this can really be helpful. For now, we're just going to take the shape and we're going to spin it to see if it looks the same. And we can see that that shape as well as this shape both exhibit rotational symmetry but don't have a certain line of symmetry. Courtney, how many lines of symmetry does this hexagon have?
That's a good question, Taylor. So what we're going to do is, we know a hexagon has 6 sides. And so we're going to start, and we're just going to draw lines straight through the middle of each part of this hexagon. We're going to have a line connecting these 2 points so that we know if we folded this hexagon in half along this dotted line, this side and this side are going to be exactly the same. We're going to do the same with the line straight down the middle, another one connecting this point and this point, and one coming straight down the middle here, one going straight across the middle here, and then one more coming through these two sides. So that shows us that we have 6 lines of symmetry in this hexagon. Maya, how can I make a vertex figure?
Okay, so when you're doing, we had a question from our homework, and it was asking if Maya's was correct. So hers was incorrect for that particular question because it didn't equal 360. So what we're going to do is we're going to have different shapes to see if we can make a vertex figure. So we're going to have a hexagon, which has 6 sides, a dodecagon, which has 12 sides, and a square, which has 4 sides. And if you add all those together by their sides, you're going to get the square having 90 degrees, the dodecagon having 150, and the hexagon having 120. And if you add all that together, you're going to get 360. So that way you know it's a vertex figure. Sarah, how do I find the measure of the angles in the octagon?
All right, so when we're looking for the angles, you might remember before, I think it was on our last lesson, it showed us how to find the measurement of each angle. So you're going to take n minus 2 times 180 divided by n. And let me get this to show you. And when we add it all up, what we do then is we're going to find out with the measurement of each shape, and then you add it together. Whenever we do that on this one, we divide each part. So it's an octagon, so we're going to have 8 different lines here, and we're going to have 8 minus 2 times 180 divided by 8, which 8 minus 2 is 6, times 180 divided by 8 gives us 135 degrees. So we know that each angle that we have here, all 8 of them, each of them are going to be 180 degrees. All right, Taylor, is this figure a vertex figure?
That's a really good question. For any group of shapes to be considered a vertex figure, we want to look at their interior angles where the shapes meet. And so that's going to be right here with these 3 shapes. And what we want is for each of the interior angles to add up to equal 360 degrees. And, well, that pulled up backwards. We use our formula that Sarah just told us to find the interior angles of the octagon, which is 135 degrees, the hexagon, which is 120 degrees, and the pentagon, which is 108 degrees. And so when we add these up, we get 363 degrees, which is not 360 degrees, which means this is not a vertex figure. Courtney, what is an equilateral triangle, and how do I find the interior angles?
All right, an equilateral triangle pretty much explains itself. An equilateral triangle is a triangle that has all equal sides and all the angles are equal measurements as well. So we're wanting to figure out the angles, our interior angles, the measurements for these angles right here. And now each side is going to be equal. So right here, these are each 10 inches long. But we don't need to know this for it to affect our interior angles. That just lets us know that it is an equilateral triangle. So if all the sides are going to be the same length, then all the interior angles will be the same as well. The best way to do that is we know that a triangle has 180 degrees total between all its angles. So we're going to take 180 degrees and divide it by 3 for each angle, and that gives us 60. So that shows that each angle is 60 degrees. Taylor, how can I find the measurements of the interior angle of this octagon?
All right, we are going to use our interior angles formula to find this answer. And so this formula is n minus 2 times 180. And this will give us this total sum of the interior angles. So that means that once we do get this number, we're not finished with this question yet. We're going to have to divide this number by the number of sides in order to find out just what one interior angle is. And so when we're going to plug in 8 for n, because n is equal to the number of sides of the shape. And so when we plug in 8 minus 2 and multiply that by 180, we get 1,080 degrees. And we're going to divide that by 8 to get 135 degrees for the interior angles of this octagon. Demia, what is the difference between the SSS property and the SAS property?
Okay, so for one of our homework questions, we had a question about triangles being congruent. And I feel like this was a huge thing to know when you're talking about the congruency between triangles. So the SSS property just stands for side by side property. And that's when the 3 sides of one triangle are congruent to 3 sides of another triangle. So when this happens, that's how you know the triangles are congruent. Versus the SAS property, which is side angle side property, is when just 2 of the sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle. So that's how you know those 2 triangles will be congruent. Sarah, why is angle QVP a right angle?
Okay, so this is a really good question. We notice that angle QVP is on the top half. So we have line M going through our line segment of P to T. So what we see here is we have 2 angles, and it's showing us that it's a right angle, but why is it? So we know that when we have a line, it's going to measure 180 degrees. We have a vertical line that intersects our line M. So that tells us that the sum of our 2 angles will be 180. And anytime that you have a vertical line intersecting a straight line, we know that it's going to be 90 degrees because we have 2 angles. The sums have to be 180 degrees. So we know, therefore, that the angle of QVP will be 90 degrees. All right, Courtney, how can you prove that triangle QPT is congruent to triangle SPT?
That's a great question. So we have the triangle QPT right here that's highlighted in red. And then we have triangle SPT over here highlighted in purple. Now this line right here down the middle is a straight vertical line. And if I were to fold this figure completely in half along this line, this triangle right here would reflect over here onto this side, lining up perfectly with this purple outlined triangle. So that tells us that all of our sides and our angles are congruent. Taylor, which triangle is congruent with QPV?
That's a good question. QPV. Okay, we're going to look at this shape, and we know that congruent triangles are 2 triangles that are exactly the same with their side measurements as well as their angle measurements. They are just the same triangles. They might be turned different ways, but they measure the same with their angles and sides. And so knowing this, we are going to use what Demia told us about the side angle side property. And we know that this little blue tick mark on the blue lines means that this line is going to be congruent or the same length as another line on the shape. And because these are both the only ones with just 1 single tick mark as opposed to these with 2 tick marks, that means that these 2 sides are the same. And so our side angle side property says that if any pair of corresponding sides and their included angle are equal, then the triangles are congruent. And so using this, we can know that triangle QPV is congruent to triangle PVS. Demia, how do I calculate angle NOQ?
Okay, so if you look here, we have 3 different shapes, but if you look closely, I have made a triangle out of the angles NOQ to kind of show you where I'm talking about. So, maybe. Okay, so for this particular one, we're going to be looking at the 2 angles, the 2 shapes, the pentagon and the triangle. So if you look at the pentagon, you know that it has 5 sides. So you're going to divide that by 360. That's going to give you 72. But you're going to also need to multiply that by 2 to get 144. So you're going to do the same thing with the triangle, dividing it by 3 to get 120. And if you subtract those 2, 144 from 120, you're going to get 120, you're going to get 24. and that'll give you that the angle NOQ is equal to 24. Sarah, can you tell me how do you inscribe a pentagon in a circle?
Yes. So here we see we have a pentagon, and it tells us our points are going to be PENTA, which is kind of clever because it's the first part of the word pentagon. So after we make our pentagon, we're going to label each of the sides that way, because that's going to be our points. So when we have something inscribed, it basically means that we're putting it inside of a circle. So let me get our circle up. And once we put it in the circle, it will look something like this. Each of our dots, our PNTA, will touch on the outside of the circle as shown. And that's how we would inscribe a pentagon. Okay, Courtney, what does the number 5 represent in this figure?
That's a very good question, Sarah. So what we have here is we see that a pentagon has 5 sides. Penta is meaning 5. So we're going to see, we're wanting to find the central angles for each angle of the pentagon. So we're going to take 360, which is what we know the measurement of the interior angles or central angles of a pentagon all equal up to, and we'll divide it by 5, which are the angles we want to find. And we'll see that it equals 72, and that will be the total amount for all 5 central angles on the pentagon. Taylor, are there any similar triangles present in this image?
That's a good question. We've been talking a whole lot about congruent triangles and not very much about similar triangles. So 2 triangles can be similar to one another when they have the same angle measurements, but they have different side lengths. So what I mean by this is that there actually are 2 similar triangles present in this image. And I'm going to pull them out to make it easier for us to see. So when we look at these 2 triangles, we can see that they look very similar. So that's why we can call them similar triangles. But when we label the angles, we can know that angle A is congruent to angle Y, angle B is congruent to angle X, and angle Z is congruent to angle Z. Demia, how can I find the height of the cliff?
Okay, so first we're going to start with what we were given in our actual problem. Maybe. Okay, so if you look here, I have set up the formula, and basically when you first start looking, you see that we're dealing with inches and feet. So first things first, you're going to want to convert everything to feet so you're not dealing with 2 different measurements. So I have the height of the cliff equals 0.125 feet times 1,320 feet, all divided by 2. And when you divide that together, you're going to get like 82.5 feet, and round that off, you're going to get 83 feet. So that is the height of the cliff. Sarah, what is 1/4 of a mile, and how do you convert inches to feet?
Okay, so to find 1/4 of a mile, we need to understand what that means first. So 1/4, you can think of it, some people say 1/4, some people say 1/4. So we know that there's 4 parts. So we know a mile is going to be 5,280 feet. So you're going to take that number and divide by 4. When you do that, you get 1,320 feet. So that right there is 1/4 of a mile. Okay, so now it says we have 1.2 inches, I should say inches, is the height of the cliff. So we want to make sure that when you're doing any problem that all your unit of measurements are the same. So we need to convert inches into feet. So how we do that is we're going to take our 1.5, divide it by 12, and it's going to give us 0.125 feet. And knowing that, as Demia showed you, you can then finish the problem and answer the rest of the questions. All right. Was that it? Did I go past somebody's?
That was all.
All right. All right, thanks for watching.